Hello students, welcome back to our channel. Students, in this video we are going to study a very important topic from class 12th physics chapter alternating current, and this topic is self-inductance. What is self-inductance? Let us write the definition first and then we will discuss each and everything appearing in the definition. It is the property of a coil by virtue of which it resists any change in the strength of current flowing through it by inducing an EMF in itself. Okay, what is the meaning? It is the property of a coil by virtue of which it resists any change in the strength of current flowing through it by inducing an EMF in itself. What's happening? Let us say that this is a coil. And this coil is suppose connected to an external battery, this through a rheostat. Rheostat is something which has a variable resistance, so it is used to change the value of current in a circuit. Now how it works? Now if I join this link on this part, then whole of this resistance goes out of the circuit, so the current will increase. Since the resistance is directly proportional to length, so if I'll join this end of the solenoid with the end of this rheostat, then the whole of the resistance will come into the circuit and the resistance will increase, so the current will decrease. So using this resistor, if we change the strength of current through this coil, so what happens? We know that when a current passes through a solenoid, a magnetic field is present around the solenoid, so which depends on the strength of the current. So if you change the strength of the current, then the magnitude of the magnetic field around the solenoid will also change. So now this solenoid is placed in a changing magnetic field. So what happens? If the magnetic field is changing, then obviously the flux through each turn is changing, and when the flux through each turn is changing, according to the Faraday's laws of electromagnetic induction, a current is induced. Now due to its own changing magnetic field, a current will be induced in this coil, and due to Lenz's law, this coil is going to oppose that change. So the coil will oppose the reason of the change. So why the flux is changing? Flux is changing because we are changing the strength of current in the coil. So this coil will oppose the change in the strength of current through itself, right? Because when you change the strength of current through this coil, the flux through each and every turn of the coil will change. So it has to oppose anything which tries to change the magnetic flux through it, because due to that a current will be induced in the coil, and that is the property of the induced current, that it has to oppose the change due to which it has induced. So the current is induced due to the change in the current, the original current in this coil. because due to the change in that original current, the magnetic field around the coil is changed. So this coil will resist a change in its own current, and that property is called the self-inductance. So it is the property of a coil by virtue of which it resists any change. We will go into the details. I know a little bit confusion is still there, so I'll just show you what is actually happening inside this solenoid. So it is the property of a coil by virtue of which it resists any change in the strength of current flowing through it by inducing an EMF in itself. Now let us take two consecutive turns of this solenoid. Now these are the two consecutive turns of this solenoid, and the current through these two turns are connected, but I am not showing the connection right now. Okay, let us show the connection. It is going like this and then this, right? So these two are two consecutive turns of this particular solenoid. So what happens? Suppose the current through this solenoid is flowing in this manner. So the magnetic field will be like this, will be what? So if I'm looking from this angle, then the current is in clockwise sense, and when the current is in clockwise sense, the magnetic field is towards the observer. No, sorry, current is in clockwise sense, so like this. So magnetic field lines will be like this. So magnetic field lines of this will be like this. So magnetic field of one turn, magnetic field lines of one turn will be passing through other turns, right? So magnetic field lines will be like this. Now suppose we are increasing we are increasing the strength of this current. So what happens? If we increase the strength of this current, so these magnetic field lines will also increase, right, which are going into the plane, into these turns like this. So if we increase the strength of the current, these magnetic field lines will also increase. So what happens? It has to resist the increase of magnetic field lines due to Lenz's law. So for that, he has to induce a current in itself whose magnetic field lines are in this way. So it has to induce a current. It will induce a current in the anti-clockwise sense. So the magnetic field lines are in a direction which is opposite to the magnetic field lines of its original current. So it will induce a current in the anti-clockwise sense, which will cut this original current. Suppose this original current was 10 ampere and we have increased this value from 10 to 12. So we have done an increase of 2 amperes. So what it will do? It will induce a current of 2 amperes in the opposite sense. So again it brings back the current to 10 amperes, right? So this is how it helps to keep current constant in the circuit, and that is its main use. This coil, this solenoid, or this inductor, we are going to call it now an inductor, because inductor is one of the most important elements of an electric circuit, like capacitor, like resistor. Now we have a third important element which is called inductor, because it induces inductance in the circuit. It introduces inductance in the circuit. So it helps to keep a fluctuating current in a circuit constant by this mechanism. And this mechanism, this property of this coil is called self-inductance, or it is called just inductance. Not just inductance, inductance, right? Okay. So there is some mathematics involved in this. We will discuss that. We can say that the flux through this coil is obviously proportional to I. More the current, more will be the magnetic field around the solenoid, and more will be the flux. So we can say that phi is proportional to I. And when we remove the proportionality sign and put an equality sign, so we will write L here, and this L is called the coefficient of this L. Like we had C, capacitance, and we had R, resistance. So this is L, which is called the coefficient of self inductance. Coefficient of self inductance or self inductance, not just self inductance, or self inductance or inductance. You can call it inductance. If you do not want to use these long names, you can just call it inductance, right? Okay. So phi is Li is a very important equation in inductance part, right? It is an equation like V equal to IR or Q equal to CV. So it is a very important equation, phi equal to Li. Okay, since we know that the EMF is what? EMF is minus d phi by dt. According to Faraday's second law, induced EMF is minus d phi by dt. So if we put the value of phi, which is Li, in place of this, we will get E equal to minus d by dt of Li, and L will come outside the derivative because L is a constant and the property of the inductor. So it becomes E equal to minus L di by dt. Di by dt. So it is a another very important formula in this case. So EMF is equal to negative of the self inductance of the solenoid into di by dt. Di by dt means the rate of change of current. So what is the SI unit? SI unit of L, SI unit of L, that is inductance or self inductance, is Henry. It is Henry, and the symbol of Henry is capital H. Symbol of Henry is capital H. How we are going to define 1 Henry? Since E is minus L di by dt. Let us ignore the negative sign for some time. So if E is 1 volt when di by dt is 1 ampere per second, right? If E is 1 volt when di by dt is 1 ampere per second, for example, if the rate of change of current through a solenoid is 1 ampere per second, and due to that rate of change of current of 1 ampere per second, suppose 1 volt EMF is induced in the solenoid, then if we put 1 in place of this and 1 in place of this, then we will say then L is also 1 in SI units, and that is Henry. So if we have to define 1 Henry, right? If we have to define define 1 Henry, so we can say that self inductance of a coil is said to be 1 Henry when an EMF of 1 volt is induced in the coil when rate of change of current through the coil is 1 ampere per second. Self inductance of a coil is said to be 1 Henry when a current of when an EMF of 1 volt is induced in the coil when rate of change of current through the coil is 1 ampere per second, right? Okay, so since E is, ignoring the negative sign, we can say that the EMF E or the magnitude of EMF E is L di by dt. So L is what? L is magnitude of E into dt divided by di. So 1 Henry also is, which is very important, 1 Henry is what? It is volt per ampere into second, right? Because the standard unit of EMF is volt and the standard unit of current is ampere and the standard unit of time is second. So we can write 1 Henry, volt per ampere is nothing. Apply Ohm's law, R is V by I. So volt per ampere is nothing, it is ohm. So 1 ohm second. 1 ohm second. So this is how Henry is related to this ohm and second. So this is a very important relation because we are going to use this relation in the next chapter at so many places. Alternating current chapter mein we are going to use this relation. So this is a very important relation. One marker can come based on this relation. You can get an MCQ based on this relation, and most importantly, you can find the dimensions of self-inductance using this relation. So this was everything about self-inductance. Definition is very important. Prepare it very carefully. I'll meet you in the next lecture. Till then, all the very best.